All right, so welcome everyone to this seminar on climate variability across scales. This is part of the PAGES working group CVAS. And as the first speaker in this lecture series that we're going to have in this winter term, we have Juerg Schmidli. Juerg Schmidli is a professor for boundary layer metrology at the Goethe University in Frankfurt. He's been for 5 years, but he began his career in environmental sciences. I think that's the English translation, right?
Yes.
At ETH in Zurich. And after after a long career there, starting as a student, as a PhD student, and then as a postdoc, he briefly moved to the US before he came to Goethe University. And he now leads a research group on boundary layer metrology. And I'm really excited that, I'm really glad that you make the start for this lecture series, where we are going to start from the smallest scales, well, small for us, for paleoclimatologists, and we're going to move progressively towards larger and larger scales in the climate system. And with that, I don't want to talk a lot more. Juerg, I'm looking forward to your presentation.
Thank you very much for the kind introduction and the invitation. It's really a pleasure to participate in this lecture series. So the topic of my presentation is variability of the short-term variability at time scales below 1 day, so from seconds to hours, with a particular focus on the near surface temperature, as it is one of the key variables of interest in this seminar series. So what phenomena lead to subdaily weather variability? At what temporal and spatial scales? Let me start with an example. So this slide shows a typical evolution of the 2-meter temperature on a nice sunny day for a semi-arid region. So this is in Owens Valley, California, which is shown on the photo here. And you see here the time of the day and the temperature. And so the well-known evolution, we have cooling during the night and then rapid temperature increase in the morning hours, slower increase later during the day, and then a decrease again after sunset. So this is well known. And of course, this is linked to the diurnal cycle of the solar forcing, here indicated by the gray curve. Note, however, that this time series has a hourly resolution. So the temperature is averaged over 1 hour intervals. What about the variability at shorter time scales? So if we go to 5-minute resolution data, one can see already more variability. So these fluctuations here during the day and even larger fluctuation here during the evening. If you look at the radiation, you can see that these fluctuations are not due to clouds. So what is the origin of this variability? And what happens if we increase the temporal resolution further? So now I'll zoom into this 4-hour period in afternoon, so between 1 and 5 p.m. local time. So this is a temperature series at 5-minute resolution. And if we go to 1-minute resolution, you see much more variability. In fact, fairly regular oscillations around the 5-minute mean. So the variability as measured by the standard deviation has increased from 0.52 to 0.77 Kelvin. What if we further increase the temporal resolution? So I zoom into just now 1 hour period here from 1 to 2 p.m. Again, the time series at 1 minute resolution. And if we now go to 1 second resolution, we have even again much larger variability. The standard deviation has more than doubled. So at what time scales does this increase in variability end? Well, I won't show it here, but if we increase, say, to 10 Hertz data, the variability increases only by another 5%. So at 1 second resolution, we capture already the major part of the variability. So to conclude, we find here A large variability on time scales from hours to the sub-seconds. And so what phenomena are causing this observed variability, and what are the associated spatial and temporal scales? More generally, what phenomena influence the sub-daily near-surface weather variability, and what are the associated temporal and spatial scales? Well, you all know the many phenomena that impact our daily weather, the weather we experience every day. Here just a few examples. So the diurnal cycle of the sun, clouds, cumulus clouds or fog, thunderstorms, but also sea and lake breezes, for instance, here, so induced by horizontal temperature differences between the cool air over the water and the warmer air over the land, or also mountain winds, which are also induced by horizontal temperature differences. So these are two examples of locally induced wind systems. So to expand a bit on a larger scale, we have, for example, the diurnal summertime convection. So this is illustrated here. So you see here Europe. And so this is a short animation of infrared brightness temperature. And if you look here, you see very nicely the diurnal. So every day the convection pops up as the land surface is heated. So a strong diurnal signal. Another example are the mountain winds, which are induced by horizontal temperature differences due to the unequal heating of the land surface. The slide here shows, the picture here shows, for instance, the evolution of the wind speed in a deep alpine valley. And you clearly see, so over several days, and you clearly see strong winds during the daytime and weak winds during the night. So clearly these wind systems have an impact on the local weather and the near surface temperature evolution. These are just a few examples. There are many, many more. So what are the associated temporal and spatial scales? So this slide gives an overview of some important atmospheric phenomena and the associated scales. I should mention this is a strong simplification. In reality, there's a much larger overlap between these different phenomena. Nevertheless, so if we restrict ourselves now to timescales shorter than 1 day, we see that the phenomena are typically smaller than 200 kilometers. So in this range, we distinguish between microscale phenomena, such as turbulence and cumulus clouds on scales smaller than about 1 kilometer, and mesoscale phenomena, such as thunderstorms or lake and sea breezes, mountain circulations, urban effects, which have scales typically larger than 1 kilometer. So in terms of processes, we can distinguish between turbulence and atmospheric boundary layer, moist convection, interactions with the Earth's surface, leading to many different types of local flows, and gravity waves. So indeed, a very rich set of phenomena and processes. And each of these could be a topic of the entire lecture series. Today, I want to focus on one key element, which is relevant for near surface weather, the turbulence and the atmospheric boundary layer. Why turbulence and the ABL? Well, it's an observation that the near surface weather evolution is strongly tied to the state and the evolution of the atmospheric boundary layer. So if we want to understand and predict the variability of near surface temperature, so for instance, a temperature 2 meters above ground, we need to understand the structure and dynamics of the atmospheric boundary layer. So the plan for today is I want to first give a brief introduction into the ABL and turbulence, followed by a discussion of the structure and the dynamics of the atmospheric boundary layer. And in the final part, I introduce a simple model for understanding the near surface temperature variability and its connection to the dynamics of the ABL. So let me start with an example. So I want to next show a time-lapse video of a typical summertime convective atmospheric boundary layer. And I invite you to focus on the 3 different cloud layers, which you can see in the video. So let me start. So you see we have the lowest layer, cumulus clouds, which are in the atmospheric boundary layer. You can see they are highly turbulent. They come and go. And above that, we see the flow in the free troposphere, which is really just quite steady, smooth, and quasi-horizontal. So the distinction between more or less laminar flow above and highly turbulent flow in the atmospheric boundary layer. So the ABL is a region from the surface to the top of these cumulus clouds. Or in other words, the ABL is the lowest layer of the troposphere, which is strongly influenced by the Earth's surface. And it responds to the surface forcing on a timescale of 1 hour or less. And the key characteristic of the ABL is that the flow in the ABL is turbulent. So why is atmospheric boundary layer important? Well, it's the region where we spend most of our life, and it's also the natural environment for most human activities. For instance, for energy metrology, as shown here on the slide, or transportation or agriculture. And if you're interested in the near surface quantities, such as 10 meter, 2 meter wind, or 2 meter temperature, or 10 meter wind, we really need to understand the structure and the dynamics of the atmospheric boundary layer. And in order to understand the atmospheric boundary layer, we need to understand turbulence. So why is the atmospheric boundary layer turbulent? Simply put, the conditions in the atmospheric boundary layer are just favorable to flow instabilities. So what are the main causes of these instabilities of turbulence? Well, the 2 primary causes are related to mechanical and thermal instabilities of the flow. Mechanical turbulence can be caused by frictional drag near the ground, the wake turbulence behind obstacles such as trees, buildings, or hills, or in free shear layers removed from this, distant from any solid surface. On the other hand, we have thermal or convective turbulence, which is related to currents of warm air rising and cool air descending due to buoyancy forces. That is due to temperature or density differences in the fluid. Note that while the wind shear always is a source of turbulence, the buoyancy forces, it depends on the condition. They can create or they can destroy turbulence. So what is the structure of turbulence? This picture here shows a transition from smooth laminar flow to chaotic turbulent flow. So one can picture a turbulent flow as a superposition of irregular swirls of many sizes, really of many orders of magnitude. These swirls are often called eddies, which is nothing more than a concise term for a local turbulent motion with a certain scale, but any arbitrary local flow pattern. So we will return to the size of and structure of turbulence later on in the presentation. First, so why is an understanding of turbulence important? And here one can distinguish in some applications when it's really interested in short-term fluctuations, extreme values, and small-scale variability. So when it's really interested in the details of the turbulence, for instance, for aviation safety, in relation to clear air turbulence, or if one in the design and siting of wind turbines, where one has to estimate the loads and the stresses on the machines. For other applications, one is really interested in the net effect of the turbulent motions. For example, the surface exchange of heat and moisture between the land surface and the atmosphere due to turbulent motions, or in the relationship between turbulent intensity and the strength of the near surface gradients. For the latter question, we need to turn to statistics, to the statistical approach to turbulence. So two key ideas of the statistical approach are, first, that we separate an atmospheric variable, for instance, temperature, into a mean, contribution, and a fluctuation. So, for instance, an hourly average and a deviation from that hourly average. So this normal mean, and let's illustrate with our previous example. So here again, the 2-meter temperature for over several hours. The gray curve denotes the hourly means, and then the fluctuation or the deviation from the mean is shown in the lower panel. Notice a different scale. So these are the turbulent fluctuations around the longer term mean. Then the second key idea is that we characterize the turbulence by the statistics of the fluctuating parts. So, for instance, the temperature variance or the covariance between the velocity field and the temperature field. Let's look at an example. So how can we measure the intensity of turbulence? For that, we return to the data from our initial example, so from Owens Valley. Here now I show the mean wind speed at 30 meters above ground, and shading you see 1 hour during the night, and so blue shading and orange shading 1 hour during the daytime. And so the question is, how does the turbulence intensity compare between this nighttime period and the daytime period? For which time period would you expect stronger turbulence? So here during night we have a mean wind speed of about 10 meters per second, and during the day only 2 meters per second. So the figure now shows the two horizontal wind components with 1 second resolution for this 1 hour interval. One can clearly see the turbulent fluctuations. And so how can we quantify these? Well, you know that very well from statistics. So we can just calculate the mean and the standard deviation from the mean. So the shading here now denotes plus minus 2 standard deviations. So that means that if the variable is Gaussian distributed, 95% of the data points should be within these shaded areas. And so using the statistics, we can summarize the state of the flow by just 4 numbers. So the mean wind speed, about 10 meters per second, and the variability is characterized by the standard deviations or variances of the 3 velocity components. And the same analysis for the daytime period. You see the mean wind speed is much smaller, but maybe surprisingly, the standard deviation is significantly larger than during the night time. So the key point, so we can measure the intensity of the turbulence through the magnitude of the velocity variances. Now, however, the velocity variances are not just a statistic, it has also a physical interpretation. It represents the kinetic energy associated with the turbulent motions. So if you recall from basic physics, kinetic energy is equal to 1/2 mass times velocity squared. And in atmospheric sciences, we often use a specific kinetic energy with just the velocity squared half. So then we can write, then we find that the sum of the velocity variances, here given here, is just a specific kinetic energy associated with the turbulent scale motions. So this is a turbulent kinetic energy, and it is a key measure of turbulence intensity. So using the TKE, we can now easily summarize and compare the turbulence intensity during the night and the day for our previous example. So you see this in the table here at the 30-meter level and the 2-meter level. And you can see that the turbulence during the night is weaker than during the day. So here we have 0.7 versus 2.4, despite the stronger mean wind speed during the night. And we also see that the turbulence is stronger near the surface during the night, and it's weaker near the surface during the day. So this was a very brief introduction to the key measure of turbulence intensity, the turbulent kinetic energy. So it's physical interpretation, it's nothing else but the kinetic energy of the turbulent motions. Now let's have a look at the second important quantity or effect of turbulent motions, namely turbulent transport. So in the atmosphere, if you have got a turbulent velocity field, then the fluctuations in velocity are often accompanied by fluctuations in scalar quantities. And so the question is, how large is a covariation of these two quantities? What is the physical meaning? So here again, from our previous example, on the top, you see the temperature fluctuations during a 6-minute period. On the bottom panel, the vertical velocity fluctuations during the same period. And so we can distinguish 4 cases. The first case here indicated by the orange shading, the temperature fluctuation is positive and the vertical velocity is positive. So this corresponds to the upward motion of warm air and therefore results in an upward transport of heat. So a positive heat flux. A positive instantaneous heat flux as shown in the lower panel. Now the second case, the temperature perturbation is negative. The vertical velocity perturbation is also negative. And so this corresponds to the downward motion of cooler air. And because minus times minus is plus, again, the net effect or the overall effect is that we have an upward transport of heat. And you can see this in the lower panel. So for most of the period, the instantaneous heat flux is positive and upwards. So the further 2 cases are when the 2 variables are anti-correlated, and that then leads to a negative or downward heat flux. So we can quantify the overall covariability by the covariance, which you know from statistics. And so if we find that the average of the product of these 2 time series, so here's the product of these 2 time series, the average is equal to about 0.3 Kelvin meters per second. And this quantity is a so-called kinematic heat flux. And in traditional units, this corresponds to a heat flux of about 300 watts per square meter. So the net effect of these turbulent motions is an upward transport of heat with a magnitude of about 300 watts per square meter. And note that we have this upward heat transport despite the fact that the mean vertical motion is 0. It can be shown then that the turbulent heat fluxes can contribute to the warming and cooling of layers of air via the first law of thermodynamics, illustrated here. And so the net result of these turbulent motions is the vertical transport of heat and other scalars, the mixing of warmer and colder layers of air to some intermediate temperature, and with respect to the atmospheric boundary layer, the heating and cooling of the ABL from the underlying surface. So with that, I want to come to the next topic, so the structure and dynamics of the atmospheric boundary layer. So how can we study the ABL? Well, this is not very different from other areas of physics. So two important avenues are measurement and modeling. What is important, so if we want to measure turbulence, we really need fast response sensors, which have a time resolution better than a second, preferably something like 20 Hertz or even higher. And two classical examples are shown here. So on the one hand, the in situ sensor, the sonic anemometer, and here mounted on a flux tower, and an example of a remote sensor, so Doppler LiDAR. The interesting thing is actually that both these instruments measure the velocity through the Doppler effect. The sonic anemometers use acoustic waves, while of course the Doppler LiDARs, it's light. The drawback of the measurements is that if one wants to get a comprehensive picture, one really needs a large measurement campaign. So the other avenue is modeling. And there are several approaches to modeling the ABL, from very expensive turbulence resolving models, such as the so-called large eddy simulation models, or LES, over 1D versions of numerical weather prediction models, to simpler bulk models, which can be very useful for a conceptual understanding of the ABL. So now I would like to address the question, what does the turbulent structure in the daytime ABL look like? And I just want to illustrate that with one example from measurements and one example using an LES model. So the first example shows you the vertical wind speed measured here by a Doppler LiDAR. So this instrument is just a vertical pointing instrument, a vertically pointing laser, which through the Doppler effect measures the vertical motion of the air in a column above its location. And we can see very nicely the alternation of upward motions, red, and downward motions, blue. And because the Doppler LiDAR requires a sufficient amount of aerosols to get a good signal, and this is usually only the case within the atmospheric boundary layer, you can also see very nicely the growth of the atmospheric boundary layer. So early morning starts to grow, and then here black, we have the formation of clouds. Now let's have a closer look at this signal as these structures. So I'll zoom in on this 1 hour period in the afternoon. And so here you have now a very nice example of a so-called thermal or large eddy. So a buoyant updraft rising from the surface right through the atmospheric boundary layer to the top of the boundary layer, to the capping inversion. So the inversion, where we have got stably stratified air, which prevents the further rise of the thermal. Now the LiDAR only gives us information along the line of sight. To get a better insight into the spatial characteristics of the turbulent field, we can turn to the large eddy simulation. So next I will show you a very short animation of the results from a LES simulation with a grid spacing of 5 meters in all 3 directions. So you can see again the vertical velocity and potential temperature. So here below the turbulent boundary layer, above the free troposphere. So the axes are similar to before. We've got the vertical axis, but now the x-axis represents the spatial direction and not time. And so we start the simulation. And so you can now see the evolution of these thermals. Here a second thermal starts to form. And between the thermals, we have got the compensating downward motion. You can also see the thermal interacting with the capping inversion and generating some gravity waves. And so this interaction is also what then eventually leads to the growth of the atmospheric boundary layer. Okay, next slide. Now we can also take a look at the horizontal structure in the convective boundary layer. So here you see 3 cross sections at different heights, so 100 meters above ground, 500 and 1000 meters. And you can see that the horizontal structures depend very much on the distance from the surface. You can also see that the typical scales of these features scale with the distance from the surface. So at the higher levels, the current structures are on the scale of the boundary layer depths, while at the lower levels, the scales are similar scale with the distance from the surface. This figure now illustrates the turbulence dynamics and the cascade of energy in the atmospheric boundary layer. So we find the production of turbulence, of turbulent kinetic energy at scales of the largest eddies, which are typically on the order of the depth of the boundary layer, which is on the order of 1 kilometer. Then the turbulence energy cascades through the medium scales, as illustrated in this figure, down to the smallest scales, which are on the order of 1 millimeter. So at any instance in this turbulent flow field, we have a superposition of eddies of many different sizes of about 6 orders of magnitude. So from kilometers to millimeters. And the important point is so that the size of the largest scales, those scales which contain the most energy and the most variance, they typically depend on the depth of the boundary layer and the distance from the surface. If we switch to the temporal domain, as illustrated here on the right, we find the turbulence peak here, typically on a time scale of several minutes, corresponding to the time scale of the largest eddies, so of the kilometer scale eddies. At the longer time scales here, there is often a gap with little variance and energy before the variance increases again in the mesoscale region. So what is the mean structure of the daytime convective boundary layer? So that is illustrated here on the right-hand side. In contrast to the instantaneous structure, we have the mean structure on the right-hand side. And so the key feature of the convective boundary layer is really the mixed layer here, where you see the mean quantities are almost independent of height due to the vigorous mixing by the large eddies. Near the surface, the turbulent mixing is less efficient, and therefore we get stronger gradients here near the surface. So we have got the increase in potential temperature near the surface. And then the top 10% of the convective boundary layer is an entrainment zone, where overshooting thermals lead to the entrainment of free tropospheric air and the growth of the ABL. So just very briefly, a few words regarding the diurnal cycle now of the atmospheric boundary layer. As illustrated here, the alternating heating during daytime and cooling during night lead to a strong diurnal cycle of turbulence intensity and the depth of the atmospheric boundary layer. So during the day, we have strong turbulence, deep boundary layers, and during the night, we have weak turbulence and shallow boundary layers. So can we capture this dynamics using just a simple model? So assume you really want to understand and predict the evolution of near surface temperature. We now know that the near surface temperature variability can be decomposed into two components: a stochastic component, which is determined by the turbulent state of the ABL, and a deterministic component, which is related to the mean state of the atmospheric boundary layer and the strength of the near surface temperature gradient. So information on near surface temperature gradients one can obtain from observations. And so in order to predict the evolution of near surface temperature, we need to know the evolution of the mean and turbulent state of the ABL. And this can actually be achieved by using quite a simple bulk model of the ABL, which provides a simple and consistent representation of the dynamics in the atmospheric boundary layer. Here, a cartoon of the different variables and processes considered in the bulk model. So you see here, gray, the true profiles of potential temperature and moisture. In the bulk model, the ABL is approximated just by a single bulk layer, as shown here by the black curve. So the temperature distribution is approximated by two variables: the mean potential temperature in the mixed layer and the temperature jump at the top of the mixed layer. Therefore, the state of the, so for simplicity, I want to focus just on the temperature, so on the right-hand side. And so in that, so the state of the ABL is determined by only three variables: the boundary layer depth, the mixed layer temperature, and the temperature jump. And the state is influenced by three processes: the heating of the boundary layer from below, so the turbulent exchange with the land surface, the heating of the boundary layer from above due to turbulent entrainment, and the growth of the boundary layer due to the entrainment of free air by the large eddies. In other words, the dynamics of the ABL in the simple model is determined by the surface forcings and entrainment. And so so here are also the equations, but I don't want to go into that. So let me introduce and finish with a small example. So the goal is to simulate a clear September day, as illustrated in the picture. So we have the site is characterized by short grass and the sandy loam soil and a geostrophic wind speed of 10 meters per second. We start the simulation in the morning, and this is a result from the bulk model. So you see here time of day and the temperature. And the solid curve is a temperature evolution of the mixed layer, so of the atmospheric boundary layer, the mean temperature in the ABL. And the dash curve is what we are interested in, the temperature at 2 meters above ground. And the dotted curve is the temperature of the land surface. On the right-hand side, you see that we also get the evolution of the boundary layer depth. So the nice thing of this model is that it really provides a complete and consistent description of the ABL within its assumptions, of course. So it gives information on the mean and also on turbulence. So for instance, you get the information on the turbulent, on the surface fluxes, the sensible heat flux, latent heat flux, and the ground heat flux, but also on turbulent quantities, such as the turbulence velocity scales. Now, this nice thing with this model, one can make experiments. So what if the site is not characterized by short grass, but by bare soil? And this is shown on the next slide. So here, orange is now the simulation for the bare soil. With bare soil, and we see that the maximum 2-meter temperature is about 3 degrees Celsius warmer than for our reference case. And one can then also go into the details and can see that part of this difference is due to differences in the mean level, in the mixed layer temperature, but part of the difference is also due to a different strength of the near surface temperature gradient. And over the bare soil side, we also have a much deeper boundary layer. So the bulk model is a powerful tool for understanding the dynamics of the atmospheric boundary layer and near surface variability. It allows us to study sensitivity to climate perturbations, such as changes in the large-scale atmospheric conditions or changes in vegetation or soil conditions. So to conclude, we've seen that the subdaily variability of near-surface atmosphere is caused by a variety of mesoscale and microscale phenomena. One of these phenomena is turbulence, which is a key characteristic of the ABL. It is caused by mechanical and thermal instabilities related to wind shear and buoyancy forces. The ABL structure and dynamics is strongly influenced by the alternating heating and cooling of the underlying land surface, which leads to a strong diurnal cycle. Regarding the spectra, important point is that the large eddies, where most of the energy and variances scale with boundary layer depths and the distance from the surface, and they have temporal scales on the order of minutes. An open question in this regard is the spectral gap. So are the characteristics of the spectral gap? So when is there a gap and when not? Near surface temperature variability can be understood as a superposition of a deterministic and a stochastic component. The deterministic component related to the external forcing and the large scale weather, the stochastic component related to turbulence and other small scale phenomena. We've seen that the near surface variability depends on the state of the underlying surface and the dynamics of the entire atmospheric boundary layer. So it is a result of an interplay of surface forcing, mesoscale phenomena, and atmospheric turbulence. And I briefly introduced the bulk model, which I think is a powerful tool to study the dynamics of the ABL. Thank you for your attention, and I'm ready for questions.